This is your presenter Asloop Mudassar, and I am presenting slide number 110 of the course on laser physics. Question is in continuation of question number 108 and question number 109 discuss the threshold conditions for space dependent rate equations for a 4-level laser system. So question 108 means slide number 108 and question 109 means slide number 109. So you see that in continuation of these previous two slides, we have to discuss the threshold conditions for space dependent rate equations. In the last two questions, we discussed the space independent rate equations for a 4-level laser system, but here we are required to discuss the threshold conditions for space dependent rate equations for a 4-level laser system. The answer is, let us define U as the normalized field amplitude of a given mode in a cylindrical symmetric cavity which stays constant along the resonator axis, which is the z-axis. The pump rate will depend on both the radial distance from the resonator axis and the longitudinal distance along the resonator axis, that is Rp. Pump rate is a function of two coordinates r and z. R is the distance of a point within the cylinder from the axis of the cylinder, and z is the distance along the radial distance, that is along the axis of the cylinder from the one edge of the cylinder, where you can take z is equal to 0, and at any point within the cylinder the distance along the axis of the cylinder will be z. Obviously, the population inversion will also be spatially dependent. Since we have pump rate which is spatially dependent depending upon the two coordinates r and z of the cylinder. Similarly, on the same basis, we can say that the population inversion will also be spatially dependent. It can be proved that the threshold condition for n, where you see that n is the population inversion, that is the difference between the population in the level number 3 and the population level in the level number 2 of a 4-level system. So it can be proved that the threshold condition for n in the space independent case can also hold for the average value of n of a space dependent case. So you see that if we want to use the same formula that we derived for the case of space independent condition, space independent pumping, here we require to take the average value of n. Then the two formulas can be used, that is the previous formula can be used for the case of space dependent. That is the formula for the space independent case can be used for the space dependent case if average is considered, which is shown in figure number 1. So the critical value of the average of the population inversion is equal to gamma over sigma into L, where gamma is the total loss within the cavity, sigma is the stimulated emission cross section, L is the length of the active medium rod. The average which I have shown in equation number 1, that is this average, can be calculated using this formula. That is the average of n is equal to the integral of n into absolute square of u into dv divided by the integral of absolute square of u into dv, where the subscript with the integral a stands for the active medium rod. That is, this integral has been evaluated over the volume of the active medium, where the integrals are evaluated over the volume of the active medium A. At threshold and below it, the number of atoms going into the upper state is equal to those decaying spontaneously. So you see that at the threshold value or any value below the threshold, that is, we are talking about threshold pumping, we are talking about the threshold population. or we are talking about the population below the value of the threshold, under that condition, the number of atoms going to the upper state is equal to those decaying spontaneously. That is the spontaneous emission. That is all the decay of the population inversion will be through the spontaneous emission, which we can show in equation number 3. That is the pumping rate R and Z as a function of R and Z can be written as the equation that is responsible for the spontaneous decay. That is, this is the spontaneous decay term. So we have n as a function of R and Z divided by tau, where tau is the lifetime of the spontaneous emission process. At the threshold, this equation number 3 can also be written for the threshold value, which is so we can say that the critical value of the threshold pumping, that is the average value of the pump rate at the threshold, is equal to the population at the threshold, the average value of the population at the threshold divided by tau. And you see that we can divide the NC value, which is shown in the previous equation, that is this value from equation number 1. We can substitute this value, replacing the average value of or critical value of NC by its value from equation number 1, and that will give us that is the RP, average value of a critical value of RP, critical value of the pumping rate averaged is equal to gamma over sigma into L into tau. So you see that here we are, when we are talking about the space dependent quantities, we are talking about the averages of the corresponding quantities. That is, we are talking about the average of N, and we are also talking about the average of the pump rate. And then under that condition, we can use the previous formulas which we have discussed in previous slides and applicable for the space independent cases. Now equation number 3, which I have just shown over here, this equation is valid for each point of the active medium, because each point can be referenced with the two coordinates, that's R and Z, whereas equation number 4 is the average result at and beyond the threshold where d phi over dt is equal to 0. That is the photon decaying from the upper state to the lower laser state is a constant, and its derivative, its rate of change will be equal to 0. We can write the steady state value, that is so n naught stands for the steady state value, and it is the value when the lasing action has started. So steady state value, so the average of the steady state value represented by the symbol O subscript O is equal to gamma over sigma into L. And you see that this is this is the value that we have written when we are at the threshold value or beyond the threshold. This value stays the same at the threshold value, and beyond the threshold value, this steady state value would be the same. Equation number 1 and equation number 5 can be combined as. So you see that in equation number 1, you will see that I have reported the value of NC over here, which is the critical value of the population inversion. That is the average of the critical value of the population inversion is given in equation number 1. And similarly, the steady state value has been given in equation number 5. And as I told you that the critical value, that is the n, that is the average of n at the critical value C is the same as the steady state value. So we can combine these two equations, and we can equate the two equations through the value of gamma. So we have on the left hand side sigma into L into average of n at the steady state value represented by the symbol O is equal to gamma is equal to sigma into L into average of the population inversion at the critical value represented by the C, symbol C. So we have this equation number 6. So which means, this means that the average gain. So you see that the term on the left hand side, which is the sigma into L into average of n at the steady state, and sigma into L into average of n at the critical value, both are actually the average gain. So which means that the average gain this or this must be equal to the total losses gamma. So gamma is the total losses in the cavity. So we have written equation number 6, equation number 6 at the threshold value or beyond the threshold value, this equation is applicable. To simplify the spatial variation of U, we assume a single TEM00 mode oscillating in the cavity with the following spatial dependence. So you see that we wanted to simplify our system. For that one, we are assuming the TEM00 mode, which is the simplest mode that we can take. And the spatial variation of U can then be written as given in equation number 7. Here we are considering the absolute square of U because we are not using U in our calculations. So we are not giving you the full descriptions, but we are here talking about the absolute value of U, which is e to the power minus r square divided by the square of the omega naught divided by the square root of 2. Where you see that the spot size is W naught divided by the square of 2. This is the spot size of the pumping beam and is independent of the longitudinal variable Z. So you see that here we are considering that U is not changing with Z and it is constant along the axis of the cylinder. That is, along the length of the cylinder, U stays constant. The simplest case for RP, that is the pump rate as a function of R and Z, is the uniform pumping. So you see that here we are considering RP as a function of R and Z. But if you take the simplest case of RP, you should consider the uniform pumping. And uniform pumping means that RP is equal to constant. And that is, RP is independent of the two variables R and Z. So this RP is equal to constant is the simplest case that we can consider as for the case of uniform pumping. The next simplest case is the Gaussian pumping distribution, which is applicable in case of diode lasers in the longitudinal mode pumping. It can be expressed as. So you see that the next simplest case that we can consider in the case of diode lasers to be used as pumping sources, and in case of longitudinal pumping mode, we can write RP as a function of R and Z, and this is the description of full expression of the field U in terms of the field U. And also you see that the pumping will also follow the similar pattern, that is C multiplied by e to the power minus r square divided by the square of W naught divided by the square of 2 and multiplied by e to the power minus alpha Z. So you see that here the dependence of Z is also shown through the variables alpha, where alpha is the attenuation constant. So capital C is a constant proportional to the total input pump power. Electrical pumping or the lamp pumping provides uniform means of pumping. So uniform pumping has been derived earlier as given. So this is the case of uniform pumping. That is, if you are talking about the transverse pumping, then you see that this is the case of the transverse pumping, which is also uniform. So RP is equal to eta P, which is the pump efficiency, multiplied by the PPE, which is the electric power to the pump, divided by A into L into H into nu MP, where nu MP is the minimum pump frequency that is required to achieve this uniform pumping. And this is the nu MP is actually the minimum pump frequency that is required to raise the atoms from the ground state, that is to raise the population from the ground level to the level number 4 of the 4-level laser system. So this equation has been reported for in equation number 107.29. So you can also see this slide if you want to know the detail of the value of RP given by equation number 9, where capital A is equal to pi into A square, and A is the cylindrical radius. And you can say that A is equal to pi A square is actually the area of the cross section of the cylindrical radius, and L is its length. Nu m is the frequency difference between the ground level and the upper laser level. For a cladded rod, the doped active medium particles are located in the region. This is the region that is represented by the variable r that goes from 0 to less than equal to the value of A. So this is the region of the cladded rod. And the undoped region is the region which holds for r greater than A. And you know that A is what is the cylindrical radius of the active medium rod. The field truncation due to the finite aperture size of the active region can be ignored. So we don't want to place the aperture at the cross-sectional area of the active medium rod, because here we are assuming that U will hold for the whole range. That is R, that is U will hold for this range going from 0 to infinity. That is the R goes from 0 to infinity. So U will be applicable in this range. So we do not need to put any aperture at the cross-sectional area of the active medium rod. Now substituting Rp from equation number 9, that is this Rp that we have shown in equation number 9, substituting this value of Rp from equation number 9 into equation number 4, and then using equation number 2 to calculate Rp, we then obtain the following expressions for the P threshold value. So this is the pump threshold value. Pump power. So this is the threshold pumping power is equal to gamma over eta P multiplied by the term H nu mp divided by tau into sigma E and multiplied by the term pi A square over 1 minus e to the power minus A square over square of W naught divided by the square root of 2. So you see that we have also discussed this equation, but I am going to show you this equation, that is the derivation of this equation using the appendix. So you see that for the transverse pumping, we have this relationship. For uniform pumping, Rp is equal to eta P times PPE over A into L into H into nu mp. I have explained this equation. The critical or the threshold pump rate, this is also, I have discussed this equation, but here you see that I am also using the subscript with the TH, which stands for the threshold pumping. This is the average value of the threshold pumping rate. This is equal to gamma over sigma E into L into tau, where sigma is the E is the stimulated emission cross section, L is the length of the active medium rod, tau is the spontaneous lifetime of the spontaneous emission lifetime, and gamma is the total number of losses within the cavity. The effective transverse pump rate is given by. So you see that the equation that I have shown over here, that is this equation. This is valid. This is the uniform pumping in case of transverse pumping. And for the effective transverse pumping rate, we have this integral which I have mentioned in equation number Q in equation number 10, question 102.13. This equation was mentioned there. And you see that here Pi is the input power, input pumping power. Eta A is the absorption efficiency. The rest of the quantities have been addressed. So this is the integral. So if you use in here over, that is if you replace Rp with Rp is equal to constant, that is Rp is a constant in the region where R goes from 0 to A and 0 otherwise. If you use this value, constant value of Rp in equation number question number 102.13 over here, replace the value Rp by a constant value over here, then you will get this value. Because Rp is constant, the rest of the quantity is also constant except dV. The integral of dV is V. And you see that I have substituted the value of PPI, which is the incident pump power, and that incident power has been replaced by the product of two efficiencies, which is the radial efficiency and the transfer efficiency to the main electrical power to the pump, which is PPE. So this is the rearrangement of the terms, and then I have replaced eta R multiplied by eta T multiplied by eta A by eta P, which is the pump efficiency. So here the pump efficiency is the product of these three quantities. You see that these equations has already been derived. That's why you can see that here the label is question number 102.14. It means that in slide number 102, I have addressed this equation. And you see that I have the value of u square, which I have mentioned in the 2 days slide in equation number 7. I have given the value of absolute square of u, which is e to the power minus r square divided by the square of w naught over square root of 2. So if you use the value of rp from this equation, that is from this equation, if you use the value of rp from this equation and the u and the value of u from equation number 7 into equation number 2, which is which I have also mentioned in the 2 days slide equation number 2, that is this equation. If you substitute these value over these two values, that is the value of rp and the value of absolute square of u, if you substitute these two values over here and solve the integral, you will get this value. And you know that this is the threshold pumping, this is the average value of the threshold pumping rate, and this is given by this expression. Here eta P is the pumping efficiency, PTH is the threshold pump power, H nu P, H nu MP. Nu MP is actually, you see that the minimum pump frequency required to raise the population from the ground level to the upper laser level. And here I have the term 1 minus e to the power minus a square. A is what I have mentioned, the radius of the active medium rod, e to the power minus a of the cladded region, 1 minus e to the power minus a square over square of w naught over square root of 2. And in the denominator, I have a pi a square L, where L is the length of the active medium rod. So you see that I have this expression of RP, which is the pumping threshold, average value of the threshold pumping rate. I have also the value of RP, which is given in equation number 6 of question number 103. So I can equate these two equations and I can solve these two equations for the value of the P threshold. So P threshold is equal to gamma over eta P multiplied by h nu mp divided by tau times sigma E, and multiplied by pi a square over 1 minus e to the power minus a square over a square divided by square of w naught over square root of 2. So you see that this is the threshold pumping rate, pumping power. So this is what the pumping power that I was talking about. So this is, you see that in the case of transverse pumping power, transverse threshold pumping power, we have this relationship. So let's go back to equation number 10. So this is what I have given you, the derivation of this equation, that how we reached this derivation. The minimum threshold power under the condition that W naught is less than A can be written as. So you see that if you apply this condition, that your spot size or your beam waist is much smaller than the a cross-sectional area or the radius of the cylinder, then under that condition, if you use this condition over here, then you will have P M thermal. M thermal means minimum threshold power. So this is the minimum threshold power to the pump is given by gamma over eta P multiplied by H nu mp divided by tau multiplied by pi into a square over sigma E. So you see that this is what we have calculated, the minimum threshold pump power. Now we can say that the saturation power is defined as given in equation number slide number 109.7. From that one, I have taken the value of the expression of saturation power has been obtained and is listed over here, which is shown in equation number 12 over here. So PS is the saturation power has this expression gamma 2 divided by 2 multiplied by the area of the beam, which is pi into r square. So the radius of the beam is this r w naught divided by the square of 2. So this pi r square, and here r is w naught over square root of 2. So pi r square is the area of the beam and multiplied by is. Is is the saturation intensity, and gamma 2 is actually the loss through the mirror number 2. So this is the expression of the saturation pump power in terms of the saturation intensity, and these are the parameters of the beam spot. Now you see that we are to do our further calculations. We are defining two things, two variables x and y. X is equal to the ratio of these two powers, where the numerator is the electrical power to the pump, and this is the MP PM thermal. PM threshold is actually the minimum threshold value obtained from the pump. So the ratio of these two. So both these quantities are actually related to the pump. This is the electrical power given to the pump, and this is the minimum threshold power from the pump. And this y variable has been defined as P out over PS. So P out is the power output from the source, from the laser, for example, and PS is actually the saturation power, which has been defined in equation number 12 over here. So x and y are actually two-dimensionless quantities. The variables and x and y are related through this relation. I am not going to give the proof of this one, but just mentioning that x is equal to y over natural log of 1 plus y divided by 1 plus beta times y, where beta is equal to e to the power minus a square divided by the square of w naught over square root of 2. Now I am going to give you a little bit of description of the variables y and x. Y gives the normalized output power. You see that P out is the output power, and we have normalized it so that we have a dimensionless quantity. So Y is actually the normalized output power, normalized with the saturation power, where X gives you the amount by which the input power exceeds the minimum threshold power. So x gives you the amount by which the input power to the pump, electrical power to the pump exceeds the minimum threshold power from the pump. Or simply you can say that it is the normalized pump power. And here normalization is done with the minimum threshold pump power. X and Y are not linearly related, and that dy over dx is an increasing function of x. The slope efficiency is thus given by. So we have obtained the slope efficiency using the expressions of x and y variables, and the slope efficiency eta s is given by the rate of change of P out with respect to PPE, that is the derivative of P out divided by dPE, that is divided by dPPE, is equal to PS, that is the saturation power, divided by the minimum threshold power P, and then multiplied by the dy over dx. So in order to obtain this equation from the expressions of y and y, I would suggest that you multiply the right hand side of equation number 14 to the left hand side of equation number 13, and similarly multiply the left hand side of equation number 14 to the right hand side of equation number 13, and then rearrange them in the form of P out over PPE, and then you will see that the term y over x will be arranged in such a way that then by inspection you can write out this expression dP out over dPPE, and this is referred to as the slope efficiency. So this is the expression that you can derive through inspection of the above two equations. The quantum efficiency eta q and the transverse efficiency eta t are respectively given by eta q is equal to h nu divided by h nu mp. This has already been discussed in previous slides, and eta t is equal to is given by the you can see that in the numerator we have a pi into w naught over square root of 2, the square of this whole quantity, which is the beam radius. So actually pi into this quantity is actually the spot size of the beam, cross sectional area of the beam of the pump beam, and divided by the pi a square, which is the cross sectional area of the cylindrical rod, cylindrical active medium rod. So here we are talking about the ratio of these two quantities, that is the ratio of the pump beam spot divided by the ratio of the cross sectional area of the active medium rod. And then again we have a factor dy over dx. I am not going to give the mathematical proof of these equations, but just consider them. So we have eta q already quoted, and then I am writing a new expression for transfer efficiency eta t. Now you see that where you have that is the eta, that is the slope efficiency eta s is equal to the product of these four quantities, which is eta p pump efficiency multiplied by eta c conversion efficiency multiplied by eta q quantum efficiency multiplied by eta t, which is the transfer efficiency. So here the slope efficiency is actually the product of these four efficiencies. These efficiencies have also been discussed previously. The expression of slope efficiency given in equation number 17, that is this equation 17, also holds for the case of uniform transverse pumping. So you see that the above case also is valid for the case of uniform transverse pumping, usually done by diode lasers. Quantum efficiency, however, is given by eta q is equal to h nu over h nu p. So for the case of laser, you can also define it that if the pumping is done with a diode laser, you can replace nu mp by nu p, which is the pump frequency. Now you see that I have also defined the value of beta over here. So let me show you the value of beta. This in equation number 16, I have given an expression for the value of beta. So I am going to talk about this. That is the ratio of W naught to A, the variable A. So when beta goes to 0, under the condition that W naught is much less than A, that is the radius of the beam spot is much smaller than the cross-sectional area of the active medium rod. Under that condition, beta will be equal to 0, and then you will get dy over dx equal to 2. For y goes to 0, or equivalently when x goes to 1. Because you see that when this is equal to 0, it means that either y is equal to 0 or x goes to 1, and the transverse efficiency becomes. So under that condition, we can write down the transverse efficiency, that is we have shown over here. This is the transverse efficiency. Under this condition, the transverse efficiency can be written as eta t, which is equal to pi omega naught square divided by pi a square, where a or W naught is the beam waist of the pump beam. So generally eta t increases with x. At low powers, that is when x goes to 1. So let me show you the expression of x. This is x goes to 1 only when this p minimum threshold value of the pump power is equal to the electrical power to the pump. So if these two terms are very close to each other, we have x goes to 1. But x only exceed 1. At x could be much larger depending upon the value of a PPE. That is, if the electrical power to the pump is much larger, then of course x will be much larger. So generally eta t increases with x. At low powers, when x is nearly 1, stimulated emission dominates near the beam axis, and the spontaneous emission dominates in the wings of the beam. When we are talking about the Gaussian beam, under this condition, that when x goes to 1, stimulated emission dominates near the beam axis, and the spontaneous emission dominates in the wings of the beam, where the intensity is weak. With the increased value of the power, that is for larger value of x, stimulated emission starts dominating the domain of the spontaneous emission region at very large powers. That is when x is very large, or in other words, when the electrical power to the pump is very large, stimulated emission is the only dominant mechanism, and the excited atoms decay only through the stimulated emission, because the spontaneous emission will be dominated by the stimulated emission. Under the condition, then when x is very large, or the input electrical power to the pump is very large. Let's now discuss the pump beam having a Gaussian distribution. So you see that previously we most of the time talked about when the pump beam was constant. So let me show you the expression. For example, here Rp is equal to constant. The next possible state for the simplified version is the Gaussian pumping distribution. So if you use this constant, you have different results. But if you are using Rp as a Gaussian beam, then you see that we shall have the following discussion for them. Let's now discuss the pump beam having a Gaussian distribution given by equation number 110 in equation number 8. So let me show you equation number 8 again. So this is the pumping. This is the pump power, rate of pumping, and you know that on the right hand side we have the Gaussian distribution, and this is along the longitudinal directions, where the parameter z is along the longitudinal axis. Okay, so let's now discuss the pump beam having a Gaussian distribution given by equation number 8, which I have just shown you. X as given by equation number 13, and Y as given by equation number 14, and PS, that is the saturation power, given by equation number 12, remains valid for the Gaussian distribution also. So you see that over that the parameters X and Y that we have defined, and the PS, that is the saturation power we have defined, these results will remain the same even when we are talking about the pumping beam having the Gaussian distribution. However, PM threshold, that is the minimum threshold power to the pump under the condition that W naught is much less than P, is however given by this relationship. That is the P minimum threshold power from the pump is equal to gamma to the pump is equal to gamma over eta P multiplied by h nu P over tau multiplied by pi into omega P square over 2 into sigma E. You see that sometimes I am using sigma E and sometimes I am simply using sigma. So sigma is actually the stimulated emission of the stimulated emission cross section, and when we are using sigma, it is actually for the spontaneous emission. Tau is the lifetime of the spontaneous emission. So if I am using sigma E or simply sigma, then you should assume that this is both are for the case of stimulated emission cross section. And for this one, you can see equation number given in slide number or question number 104.3. And I think that I have also given in equation number in the appendix. For example, over here. So this P threshold value and the long mean longitudinal along the longitudinal pumping value. So the threshold longitudinal pump power is given by this relationship. And you see that here I have this one W naught square plus WP square, where W naught is the beam waist at the is the radius at the beam waist, and WP is the value of the beam radius at any other value along the longitudinal direction. So here you can assume, here you can make an assumption or approximation that I am going to address. For example, over here, under the condition that W naught is much less than WP is given by this relationship. So if you apply this relation, that the formula that I have just shown you in the appendix, you will obtain this formula. So this is the minimum threshold power to the pump obtained from the pump. So this is the formula that I have written. And X and Y can also be related through this relationship, which I am not giving you any proof for that one. So 1 over X is equal to the integral from 0 to 1, and then you have t raised to the power delta, and dt is the variable, integral variable, and then we have in the denominator 1 plus y into t. So this is also the integral relationship between the variables X and Y, where delta is equal to W naught over WP, the ratio of these two radii of the beams. The delta is actually the square of this ratio. For W naught less than WP, that is at the beam waist, the radius is much smaller than the radius at other positions. You can consider delta to be nearly equal to 0. And equation number 22 reduces to equation number 15. So this is equation number 22. This equation will reduce to equation number 15. That is this equation. So actually both equations are the same, but under the conditions that we are using. This is the condition that we are using over here, that W naught is much less than WP. Under that condition, equation number 22 and equation number 15 becomes identical. When W naught is much less than A, or when beta goes to 0. So the equivalent conditions is also that W naught is much less than A. This is also the same conditions, because you can replace R by A. A is also the diameter of the cylinder, sorry, is the radius of the cylinder. And but you see that this is the fixed for the value of R is equal to A, and under that condition you will see that beta is also equal to 0. And this is beta equal to 0, we have also established earlier. For very small beam spot sizes, the uniform or the Gaussian pump distributions produce equivalent results. So you see that here you should consider very carefully that we are talking about very small beam spot sizes. The uniform or the Gaussian pump distribution produces equivalent results. For W naught equal to WP, it simplifies that delta will be equal to 1, and equation number 22 reduces to this. So if you use the condition that W naught is equal to WP in the definition of delta, and substitute delta over here and solve this equation, you will get the result which is shown in equation number 23. So this is another relationship between the variables X and Y. Eta X, you know that X and Y are the ratios of the powers that I have just defined, in this slide. Eta S, which is the slope efficiency as given by equation number 17, would still be valid. For transverse pumping, eta Q is equal to H nu over h nu p, and eta t is equal to pi w naught square over pi wp square multiplied by dy over dx. Here you see that we want to make a little bit comparison. It can be found that for x is equal to 10, so we are assuming a very large value, that is we are assuming for this value only stimulated emission is possible. That is the decay will not be through spontaneous emission. So it can be found that for x is equal to 10, which is a very large value, and for w naught not equal to wp, then transfer efficiency eta t for a Gaussian pumping is less than the same efficiency for a uniform pumping. So the Gaussian pumping efficiency will be smaller than for the transfer efficiency for the case of uniform pumping. That is eta t is the in case of Gaussian case is slower than eta t in the uniform case. This is due to the lower power absorption in the wings of the Gaussian function compared to the uniform distribution. Eta s, which is the slope efficiency, is equal to eta p into eta c into eta q into eta t, would still be applicable for sufficiently high power when x is greater than 7. Eta t for the two cases, that is for the Gaussian case and for the unique case, is about the same. So you see that up to this value, that is the pumping for the two values are the same when greater than that one. But you see that I have shown that for when x is equal to 10 or greater, then of course the eta transfer efficiency will be smaller than for the Gaussian case will be smaller than that of the same efficiency for the uniform pumping case. At large x and under the condition that W naught is of the same order as WP, eta t would reach 94%, and further increase in laser spot will not be useful because then P minimum threshold power or pump power becomes proportional to W naught square plus WP square. So we then otherwise you see that if we further assume any if we make any other assumptions, then of course we will also result or we shall end up with increased value of the minimum threshold power pump power. So we want to keep this pump power for greater efficiency to be smaller. The condition that W naught is of the same order as WP at large x, called the mode matching condition, gives optimum results. So you see that under the condition that W naught is of the same order as WP, and for large x values, the condition is called the mode matching condition, and this will give you the optimum results in terms of efficiency and in terms of the minimum threshold power. We have expressed absolute square of u to be equal to e to the power minus r square over square of W naught divided by square of 2. This is what we have already discussed in equation number 7, where there is no dependence upon the variable z, and we have ignored the standing wave character of the mode. So you see that using this value of absolute square of u as reported in equation number 7, it means that we have ignored the standing wave character of the mode, which can be accommodated if absolute square of u is given by the following relationship, as shown in equation number 24. That is, absolute square of u is proportional to this term, again the same term as in the previous case, and we have multiplied it with the additional term which is cos square of kz. So in the expression of u, only cos of kz will appear, but in the expression of u mod square we have cos square of kz. Equation number 7, that is which shows only this part over here, is correct for a unidirectional ring resonator. But for two mirror resonator, equation number 24, that is this equation, will be appropriate when laser oscillates in a single longitudinal mode. So you see that the simplest case is that we assume that only a single longitudinal mode is present in the laser cavity. And for a two mirror resonators, then the expression that we should use is this expression. Because in this way we can accommodate the standing wave characteristics of the single longitudinal mode also by using this expression of absolute square of u. For a mode with uniform transverse profile, the slope efficiency can be expressed as. So you see that this is the case of a single longitudinal mode, but we are using here the uniform transverse profile of the pumping. Then we have this expression, that is the slope efficiency eta s is equal to eta p into eta c into eta q into eta t into eta l. So we have, you see that we have additional efficiency being multiplied on the right hand side is eta l. So what is eta l? Where eta L is known as the longitudinal efficiency or the longitudinal utilization factor of the pump distribution. Just above threshold, the stimulated emission is dominant around the peaks in the standing wave pattern, whereas the spontaneous emission is dominant near the zeros of the standing wave pattern. So you see that here we have given very clearly that where the standing wave peaks occur, then of course this stimulated emission will be dominant around those peaks. And in the standing wave patterns where we have the minimas, the spontaneous emission is dominant near the zeros of the standing wave patterns. And here eta L is actually known as the longitudinal efficiency, and it takes care of the longitudinal utilization factor of the pump distribution. An increase in eta L occurs with increase in X, that is increasing in energy density. So if you want to increase X, it means that you are increasing electrical power to the pump. That is electrical pump power you are increasing, and when you are increasing, it means that you are increasing the energy density within the resonator, and then this will result in an increased efficiency of the longitudinal pumping, and you have eta L there, also an increased value of eta L. So an increase in eta L occurs in with an increase in X as the atoms around the field modes start decaying with increase in stimulated emission. As the atoms around the field modes start decaying with increase in stimulated emission. So when the stimulated emission will increase, then of course the number of the field modes as the atoms around the field modes. Okay, so all those atoms which are present in different field modes, you see that they could be suppressed, and only the mode which at which the stimulated emission occurs, that will be dominant. It is found that the expressions for threshold inversion represented by the critical value of the average of the population inversion, average of n at C, and the threshold pump rate represented by the C of the average pump rate, that is the critical value of the average pump rate, are identical in space independent and space dependent cases. So you can notice that these two expressions would not change. So for the space independent and for the space dependent cases, these two expressions would stay the same, which also holds when the standing wave pattern of the mode is also taken into account. So if you express u in order to accommodate the standing mode pattern, that is rather than expressing u mod square by this formula, if you express u mod square with this formula, so that you can take care of the standing wave characteristics of the mode also, then of course these results, that is these two results, that is the threshold in critical value of the average of the threshold inversion and the critical value of the average of the threshold pumping, these two results would also stay the same when we consider the standing wave patterns of the mode taken into account. The results for eta s for the two cases are directly related. The output power calculations, however, above the threshold are, however, complicated and quite different for the two cases. That is, for the space independent cases and for the space dependent cases, the output power calculations and the expressions would be quite different. So this is end of slide number 110.